Okay, in this cast, we're going to learn how to linearize data through recognition. Okay, um, before we've already seen how to get a mathematical relationship for data that's linear. So if we have circumference and radius, if you plot the data, it's going to form a straight line, and we know by using the slope rise over run formula, we can get the equation and then get the mathematical relationship. Very often in physics, the relationship between two variables is not linear, but we still do want to get the general equation. So there's different ways of doing this, and one basic way of doing this is to linearize our data. Okay, so if the relationship is not linear, we're going to replot the variables so that it does give us a linear relationship. How do we do that? Well, let's see. So here in this example, we have a and r, and if I plot those two variables, it's not linear. So the first thing you have to recognize is when data is not linear, do not try to put a straight line through the data because that just wouldn't make sense. Okay, so the step one is notice or recognize what type of relationship this is. And we already learned that something that looks like this, like a quadratic, is a square relationship that has the general formula a is equal to mr squared. Okay, the next thing is you want to get that constant of proportionality. Means what two things will give us a constant value? Well, if we rearrange this such that a is on top and r squared is on bottom, that will be equal to our slope value, which is that proportionality constant between a and r squared. Not a and r, but a and r squared. Okay, so the third thing is we need to replot. And because the ratio of a and r squared is constant, if we put a as the y-axis and r squared as the x variable, when we plot these new values, we'll get a straight line, which we are now able to get the slope from. So in this case, we can use Excel and we can get a slope of, say, 3.14. Once we have that slope, we can sub it back into this equation, which tells us that a and r squared are related by a constant of proportionality of 3.14. So our equation is a is equal to 3.14 times r squared. Okay, and this is okay. So we went from a general equation. The goal was to find this value for m, and we've done that by replotting variables and finding our constant of proportionality. So in another example, let's look at if we plot I and R. This is current and resistance, but who cares what that is right now. So what we notice is that this is not linear. Okay, so do not put a straight line through this. It's not linear. So what's the general equation? Well, for an inverse, this is an inverse function, which is y is equal to m over x, but our y variable is I is equal to m over the x variable, which is r. If you rearrange this, so to make it more clear, this is the same thing as I is equal to m times 1 over r. Okay, so step 2 is to write it as a ratio such that we get a constant of proportionality. Well, if we go I divided by this thing, which is 1 over r, that gives us m. Okay, so now we would need to replot our variables such that we get a straight line and the slope is constant. Well, we can do this if we put I as the y variable and 1 over r as the x variable. Then when we replot the variables, we get a straight line, and the constant of proportionality is going to be that slope m. Let's say the slope is going to be 5. I'm just making that up. Once we find that through Excel or whatever, or even by hand, we can sub it back into this equation, and we will get I is over 1 over r is equal to 5, which is I is equal to 5 over r. So we started with a general equation, which we didn't know the m, and we found the actual equation. Okay, so I'm going to show you a quick example with area and radius again. This is of craft circles, but that doesn't matter. The idea is I want to show you how to do this on Excel, which takes a little bit of practice, but it's nothing to really worry about too much. After some practice, it's not too bad. Okay, so again, we know how to put R here and A there. Capital A, that's our variable, so this is our X variable, and A, our Y variable in B. So we have 0, 1, 2, 3, 6, 10, 15. Okay, and for A, the area, we have 0, 3, 11, 28, 101, 331, and 701. Okay, and the idea is if we plot this, which we already know how to do, so you can do this really fast after a while, you get a square relationship. Okay, so we don't want to put a straight line through this, because I mean we could. You can go layout, trend line, options, linear. Okay, but does this look like it fits the data? Well, not really. Okay, so we don't really want to do that. Undo. Okay, so what we want to do is we want to linearize this. Okay, so what we saw already in our notes is we saw that it's a square relationship. Okay, so if it's square, to replot the variables we need A as the Y and R squared as the X. So we can do this really easily in Excel. Okay, so our X variable, we have to take the square of it. So this would be R squared. Okay, so to square these values, we can go individually, 0 squared, 1 squared, 2 squared, 3 squared, but we don't want to do that. Excel is really cool that way. We can just put a formula which says equals. This cell here is A2, so notice how column A, row 2 in the highlights, and shift 6 squared. Then we put a little check mark, and it calculates A2 squared. If we take this cursor on the variable and see how the cursor changes here, okay, make sure it changes to across, click, hold, drag down, and what it does is it takes the square of each of these values and puts them in a row for you. So you can see the formula is A4 squared, so it takes A4 block and squares it, then this one's A5 squared, so it does it really quickly. The Y value we want the same. We want A as the Y value, so we can just say that equals the B2, because this one here is in B2, so that equals to B2. Enter, or check mark, whatever, and then you again go to the corner, make sure the sign changes, click, drop, and drag down, and you get this. Okay, then when you replot this, okay, our new variables are A and R squared. When you put a scatter, look, you get a beautiful straight line. And then you do all your things to make sure this is a nice graph. Okay, you put a line of best fit through 0, 0, display equation on chart, close. Okay, now our we can get rid of this, we can get rid of that. Our axis titles. So this is just quickly. Now this is not R. Our X value is R squared. Okay, our Y value is axis title, vertical, rotated. Our Y value is A. Okay, and of course I'm forgetting units here, so I must put in units. Let's say that's units of meters squared, and this is also of units meters squared. Meters squared. Okay, so now we also have to change this. Y is equal to area, that's our Y variable, and our X variable is equal to R squared, and this is too many sig figs, so maybe we want to just 3 sig figs, and there we go, we have a beautiful graph and our final equation. The last thing I might ask is, what is the meaning of the slope? Well, not what the meaning of the slope is, but what's the unit of the slope. In this case, the Y unit is meters squared. This thing is meters squared, so we'll get meters squared divided by meters squared, and the unit, which would cancel out, so the unit of the slope in this case is unitless, and we know that that's pi, which doesn't have any units. Again, we'll have more experience with this in class.